Chapter 2, Lesson 3 of Advanced Algebra, and in this lesson we're going to look at a special kind of linear equation called a direct variation. And we're going to talk about some vocabulary in here that will also apply to the next lesson, so we'll kind of marry these lessons together and treat them as one, even though they're separate. So we'll look at writing a direct variation and then interpreting a direct variation, and then we'll look at using direct variations in proportions. So the first thing we want to talk about is this, is that a direct variation is a form or a type of linear equation. Now we just talked about linear equations and we talked about slope-intercept being the equation y equals mx plus b. In a direct variation, it's a special type of linear equation, and this is what makes it special, is that the y-intercept is 0. So the y-intercept for every direct variation is 0. So the line passes through the origin. So because the y-intercept is 0, you can imagine me putting in plus 0 out here. We wouldn't have to write that because adding 0 won't change this. So we'd be left with just y equals mx. And that's what a direct variation is. Now, the direct variation equation that we're going to use is y equals kx, and all we've really done here is replaced m with k because we want to call, or we talk about this slope as being the constant of variation. And so to kind of make it line up with what we're saying, constant of variation, we use the letter k, but in actuality it really is simply the slope, the rise over the run. Okay, so it's a special type of linear equation, so we have the form y equals mx, okay, but we're going to use k because we're going to talk about what this letter k means, and it's called the constant of variation. Now we can identify direct variations either by looking at a table of values or at the equations, and we'll look at these separately. Now one last thing before we look at a table about direct variations, one way to kind of get an idea of a function possibly being a direct variation. It's not always guaranteed, but one possible characteristic would be that if the x values are going up and the y values would also be going up, you may be looking at a direct variation. Now it's not always the case, but it is a way to distinguish whether the table you're looking at could be a direct variation. You look at the x values, if they're going up and the y values are going up, then it's possibly a direct variation. Or if the x values are going down and the y values are also going down, then it could be a direct variation. We still have to do some calculating to make sure, but that can give us a sense of maybe if it is or not. Now, in a direct variation from a table, if we took the original equation y equals kx and we did some algebraic manipulating like we did earlier this year with variables, and we solved this for k, we would come up with this equation here. So actually, if a function or a table is a direct variation, then if you took all of the ordered pairs and you put the y value of each ordered pair over its corresponding x value, you'd always get the same number. And that's why we call this the constant of variation. The y over x is always the same. So we can check that from a table by simply substituting the y and the x into the expression and see if we get the same value each time. So if we took a table here, we notice that the x values are going up and the y values are also going up, so this could be a direct variation. So we're going to take the y value and see if we get the same thing when we put it over all the corresponding x values. Okay, so here's my y value for the first order pair of 9 over 27, and we reduce that, that's 1/3. The second ordered pair, we take 10 over 30, reduce it to 1/3. The third ordered pair, 20 over 60, reduces to 1/3. You'll notice that this is always the same. It remains constant. So this actually is then a direct variation because every ordered pair produces the same constant when you put y over x. Now this number that we get is the constant of variation. So we know what k is now, so then we could write the equation. So in a problem like this, you have three things to do. Determine if it represents a variation, and we did. The answer is yes, so you want to write that answer. It says next give the constant. The constant is 1/3. It then says to write the equation. So the equation, you remember, is y equals kx. We now know what k is, so we put in 1/3. So this is the equation for the direct variation represented by this table. So you'll always have those three things to do whenever you're doing this type of problem. So make sure you do that for each one. So let's go ahead and take a look at one more example real quickly here. The x values are going up, the y values are going up. Could be a direct variation, but we need to check all of the ordered pairs. So -2 over -1 is 2. 4 over 3 is 4/3. Now I don't need to go any further because these are not the same. So I don't get the same value when I put y over x, so therefore this is not a direct variation. Alright, so that's how you would use a table to determine if it's a direct variation. Now we can also use equations to determine if it's a direct variation. In an equation we have to think about this. Y is equal to kx, and remember this is a form of y equals mx, and except for there's a plus b. Now because this is 0 out here, we don't have to write it, so our equation looks like y equals kx. So if I have a b out here other than 0, then it's not a direct variation. So we're going to have to put our equation in slope-intercept form, and if the b is 0, meaning it goes through the origin, then it is a direct variation. However, if there is another value out here besides 0, then it is not a direct variation. So it's simply a matter of doing some algebraic manipulation and then determining if we have a b value other than 0. So we're going to solve this for y. So I'm going to multiply both sides by 3. Alright, because that's going to make that reduce, leaving this as y, and that's going to make this over 2. So y equals 5/2 x. There is no y-intercept, or actually the y-intercept is 0, because I don't have to write that. Therefore, this equation is the equation of a direct variation. Okay, and then the constant of variation would be the value that's next to x once we solve the equation and put it in slope-intercept form. Alright, let's do one more here. So y minus 6x is equal to 0. We solve it for x, or for y equals, we have plus 0 out here, which means we don't have to write it. There is no b, so this is a direct variation, and the constant of variation is 6, because that's the slope of this linear equation. So you can use either tables or equations to determine whether they're direct variations, and that's what we want to be able to do in this first lesson.